All right, we are back. This is Stats 260, and we are looking at Review 3. So let's take a look. Number 1, if a sample of size 70 is taken from a population with a mean 28 and a standard deviation 9, what does the central limit theorem tell us about the mean and the standard deviation? Well, the mean would be the same. So the mean is the same for the population and the sample. So if mu is given as 28, that means we can also use x bar as 28. So the mean of the population and the mean of the sample are both 28. The standard deviation is different. The standard deviation, you think of it as like the ocean, all the fish in the ocean. There's really, really tiny, and there's great white sharks, you know, it's a lot of variation. And standard deviation is a measure of spread. So if I were then to section off a pond-sized piece of the ocean, the mean would be about the same, but the standard deviation would be a lot less. You know, if there were only, in this case, 70 fish in there. And so the standard deviation, how spread out that is going to be much smaller. And so what we do for that is we take the given standard deviation and divide it by the square root of the sample size. And so in this case, 9 divided by the square root of 70. And so that would be 1.076. So a lot less on the standard deviation when there's a sample, okay? Number 2, highlight the two main differences between a standard normal distribution curve and a t-distribution. It's got a lower peak. The t-distribution has a lower peak. So it's a little flattened down. It's like you squish down the curve a little bit. And it has a variance that's greater than 1. And the reason that the t-distribution was developed was actually for smaller sample sizes. All right, number 3, approximately what percentage of normally distributed data will fall within 1 standard deviation above and below the mean? That would be 68%. The rule is 68%. For 2 standard deviations above and below, it's 95%. And for 3 standard deviations above and below, it's 99.7%. Number 4, if we use the same sample to form both a 90% and a 99% confidence interval for the population mean, which confidence interval is wider and why? Well, the 99% would be wider. 99% confidence interval would have to be wider because if we replicated it 100 times, 99 out of those 100 would actually capture the true mean and 1 would miss it. Where the 90, so that's like wider and wider and wider and wider, the 90% is going to be less. It's going to be a smaller interval, but that means out of 100, only 90 would capture the true mean and 10 would miss it. And the reason it is because it's not as wide of an interval. And so the 99% confidence interval is wider because it must capture the true mean 99 out of 100 times. If you replicated the process a bunch of times. All right, let's look at number 5. So number 5, they're talking about a skewed distribution. So when we have a skewed distribution, what that means is it's probably got outliers, like things that don't match. So if it's skewed, when a distribution is positively skewed. So think about the skew as like if you had children's blocks and you stacked them all up and you whacked them and a few blocks went flying over there, you would have it where most of the blocks are here, but some of them went flying and caused outliers. So see, this is not a symmetric curve anymore, all right? And so if it was skewed negatively, then it would look like flipped. It would be low and then it would have a big bump at the end of it, all right? So with this, the way that these work, the curves work, is the tallest point is always the mode. All right, and we learned in the earlier chapters, the mean is not resistant, meaning if there's an outlier, it'll mess up the mean. It'll give you not an accurate mean. So I'm going to exaggerate it and say the mean is way up here. Okay, so the mean gets pulled towards where the outliers are. And then the median is going to be really close to the mode. It is a resistant, but it'll still be just a little off because it's not symmetric. Median is equal areas. So this area would have to equal this area, and that would be the median. So the mode is the highest point of the curve. The median is equal areas, and the mean gets pulled towards the outliers. All right. Okay, so then they have multiple choice here. What order would it be in? Well, it looks like it would be mode, median, and mean, which is choice B. All right. Number 6. What is the default p-hat? So if you don't know p-hat and you're given a problem, you just default it to 50%. 0.50. All right, number 7. So 7, they want us to basically look at the principle that we talked about in number 1. So first, they said, all right, suppose the population mean of cheetahs 70 miles per hour for top speed of cheetahs. Standard deviation is 8 miles per hour. Again, population standard deviation. And now for part A, they said, okay, so in the population, what if you had a slow cheetah? Its top speed was 62 miles per hour. What would be the z-score? So we do z is equal to 62 minus 70 divided by 8. And that is negative 8 over 8, and that is negative 1. So there's one standard deviation below the mean for the population, all right? Now, they give us a different cheetah. There's 40 cheetahs, and it has an average top speed of 64 miles per hour. And so what would the z-score be for that? Well, now think about it. That's out of 40, not out of the entire population. So you're in a much smaller sample. So, and it's different. It's 64 minus 70, but it isn't divided by 8 anymore. It's divided by 8, which is also divided by the square root of the sample size, which in this case is 40. All right. And so with that given, that is negative 6. And if you take 8 divided by the square root of 40, you get 1.2649. And then when you actually divide that out, you get negative 4.74. And so that would be way lower than if you looked at the entire population. So because it's a sample of 40, we're negative 4.74 standard deviations below the mean. All right, because that 40 works into this standard error. Okay, let's look at page 2. Let's see, how are we doing for time? Good for time. We'll do page 2. And so here we're talking about how old cars are in the US. And so they have an average, so they're giving us a population average of 8.3 years. So that's mu. And then a standard deviation of 0.7 years. And now they want us to draw and label a standard normal curve with all of the actual information in it, okay? So 8.3 goes here. 1, 2, 3 standard deviations above the mean. So if I add 0.7 to that, 8.3 plus the standard deviation, 1 standard deviation above the mean, this is z equals 1, but it's actually 9, and then I add it again, that's 9.7, and then I add it again, that's 10.4. Okay, and then 1, 2, 3 standard deviations below the mean, so 8.3 minus 0.7, that's 7.6, and then minus 0.7, that's 6.9, and then minus 0.7, that's 6.2. And so this would be what it would look like with the actual data in there, you know, spread out. All right? Now, letter B, it says, okay, for that problem, why don't you go ahead and find the probability that X is greater than 7 years and draw a different picture. So here, we're going to draw a picture. There's our standard normal curve. 7 would happen like right about here, so we'll put it down here. And then they want it greater than, so it's this area up in there. All right. So now we find the z-score. And so that is 7 minus 8.3. So what they gave us, minus the mean, divided by the standard deviation. So this is based on the population. We didn't have to do anything with there isn't a sample size or anything. So negative 1.3 over 0.7, that is negative 1.857, which is z equal to negative 1.86. On Alex, whenever you find a z-score, they make you round it to hundredths. Okay, and that's so you can use the chart, because on the chart it's to hundredths. All right, so we're not done. That is the z-score. It is almost 2 standard deviations below the mean. Negative 1.86 is z, but we looked that up on the chart. So we grab our charts, we go to table E, and negative 1.8 you find on the left side, and then you follow it over until there's a 0.06 on the top. So that is 0.0314. 0.0314, about 3%. But when I look at this, that doesn't look like 3%. That looks like way more than 3%. Well, that's because the 3% is this unshaded area right there. So to find our answer for this, we're going to do 1 minus 0.0314. All right, and that's going to give us our 0.9686. And then change it into a percent. So 96.86%. So the probability that you have a car that you grab and it's greater than 7, it's, you know, there's a 97% chance of that. All right. Okay, let's look at C. C is tough. C is tough for a couple of reasons. So let me erase this so we have enough room to do it. All right, so letter C is find the age of the car that would give you the 84th percentile. And so this is tough for a couple of reasons. One, they didn't give us a z-score. We have to figure out what z matches with 840. So 0.8400. We're going to use our chart, but we're going to kind of use it backwards, all right? And so what I mean by use our chart backwards is we're going to look up in this area 0.8400. There isn't one. There is a 0.8413. That is 1.00. Or if you decided to use 0.8389, you could do that. That would be 0.99. So either one is fine. They're both really close to 0.8400. So I'm going to use Z equals 0.99. If you used 1, that's fine. But that goes with the 84th percentile. Now, why did I do that? Because we have this formula, Z is equal to X minus mu divided by the standard deviation. And now look, that's 4 variables, but we have 3 of them. We have the 0.99, and we have the 8.3, and we have the 0.7. All of that is given, all right? And so now, this is tough because you had to use the chart backwards, then you had to sub it into this equation, and now you have to get your algebra on and cross, multiply, and solve. Remember, like how to do a proportion? So 1 times x minus 8.3 is x minus 8.3. And 0.99 times 0.7 is, what is that? 0.693. Okay, and now you have to solve for x. So that means isolate the variable. That means it's x minus 8.3, but we want just x equals. So we add 8.3 to both sides. And so we end up with 8.993, and then it says round to the nearest year, or it will say round to the nearest year on the test. So 9 years. Now, had we used 1 instead of 0.99, which was also very close, if we used z equals 1.0, that would have been a little easier. It would have been 0.7, and we would have added the 8.3 and gotten 9, and we wouldn't have had to round. Okay? So that was a tough problem. All right, let's look at number 9. So that is find a 95% confidence interval when they have 1,500, n is equal to 1,500, and p hat is equal to 0.42. So let's write down that equation. So a confidence interval for a proportion or probability is going to be this, p hat minus z. Now I know it says this, z of alpha over 2, but I want you to just cross off the alpha over 2. We don't care. That's just your z score. Just think of that as your z score. Don't worry about the alpha over 2 thing. Times the square root of p hat q hat divided by n. So we've got that. And then less than p hat plus this exact same thing, z times the square root of p hat q hat divided by n. Okay, so this part of it is called the margin of error. This is this piece, z times the square root of p hat q hat over n. That's called the margin of error. Okay, margin of error. Mo, hey Mo. All right, so let's put in our values. We have this is 0.42 minus z. We have to look up again on our chart. 95% confidence. So you go to table F. So we're going to table F, and we're looking on table F. We're going to 95, and then we're going all the way down to the bottom. That is 1.960. So that's where that came from. And then the square root of 0.42 times 0.58. How did we get 0.58? That's Q. Remember, if P hat is 0.42, and Q hat is 1 minus 0.42, is 0.58. And then divide that by 1500. That's less than P, that's less than. Now, for this, let's just leave that blank for right now. Okay, so we find the margin of error. In other words, I multiply this, I multiply that. Let's see, did I do that? Here. Okay, no, I did that on a separate sheet. So when you multiply all of this out, this, and then take the square root, and then take a 1.96, you should end up with 0.024978. That is the margin of error. So about a 2% margin of error. 0.42 minus that. Less than P, less than, now for this, it's 0.42 plus the same thing. So you don't do this calculation twice because this part is just that margin of error again. So it's just this number again, 0.02, let's round to thousandths, 5. Okay, so 0.42 minus 0.025 and 0.42 plus 0.025. So on this side, this side of the confidence interval, it's 0.395 is less than P, which is less than 0.445. And that is our 95% confidence interval. So what does that mean? That means that if we repeated this 100 times, 95 of these intervals would actually capture the true proportion of the problem. And we're never going to really know that. That's why we build a confidence interval. Okay, you don't actually know the true proportion of the population. And so that's an estimate for it. So this is a 95% confidence interval. If I would have said build a 90 instead of, so we'll round, that's 40 to 45. If I would have said build a 90% confidence interval, it would be smaller. So it would likely be like 41 to 43. If I said build a 99% confidence interval, it would be wider. So it'd probably be like 32 to 48 or something like that. So when you up the number and don't change anything, so if I go from 95% confidence to 99% confidence, the interval gets wider. If I go from 95% confidence down to 90% confidence, the interval gets smaller. All right? Okay, let's look at number 10. It's really the same problem. We just have to find P hat ourselves first. So n is equal to 700. It says 145 people play chess. So 145, 700. So you divide 145 by 700, and that gives you 0.207. So that's about 21%. And that means Q hat is 1 minus that, which is 0.793. All right? And so now it's just, it's plug and chug again. We're just going to plug and chug. So we're going to take this and put in our values. They want 90% confidence interval. So on our chart, on that table, you look at 90% on the top where it says confidence interval. You follow it all the way to the bottom, and it kicks out 1.645. And then we got the square root of 0.207 times 0.793 divided by 700. And that's less than P, which is less than P hat plus the margin of error. Okay, so I'm not going to write all that out again. It's just the margin of error. This is the margin of error. So we do 0.207, and that works out to be 0.025. That's just coincidence. It's not always 2.5%. Minus 0.025 is less than P, which is less than 0.207 plus 0.025. All right. And so we end up with a confidence interval of 0.182, about 18%, to about 23%. And that is a 90% confidence interval. about teenagers that play chess. All right. And then the last one on this page, 10B, is again, just plug and chug. You just look in your equations on the formula sheet. And n is equal to p hat q hat times z over e squared. Don't forget that squared. That gets left off a lot. Students kind of mess that up. So they want to know, how many do I have to ask if I have a certain margin of error that I want? And so this is kind of in the setup stage of an experiment. So find the number of teenagers that would need to be surveyed for 90% confidence interval for a proportion having played chess a margin of error of only 3%. So if the error can only be 3%, we change that to 0.03, so it's just a number. And now we put in all of the stuff we already know. So we know the 0.207 p hat. We know the q hat, 0.793. Z we have to look up. That's for 90% confidence. That was still 1.645. And then divided by 0.03. And then don't forget to divide that and then square the result. That ends up getting overlooked a lot. So n turns out to be 493.55. So if you want it to be 3% or less, we'll take that up to 494. Okay. So even if it was 493.1, we would still take it up to 494, because the higher the number, the more the accuracy. All right. So that was page 1 and 2 on the review.